And it's exactly what it sounds like. It's an exponential with something complex somewhere. I mean, you guys already know what complex numbers are. That's not new to you, right? Right? So as a reminder, so complex numbers, it starts out with a solution to this polynomial equation. X squared plus 1 is equal to 0. The solution to this is where you get complex, the imaginary numbers from. The solution to this is x is this new number, I, which has this property that when you square it, you get minus 1. Right? Nothing here is new. I squared is minus 1. So, so that's a solution to this. And you have seen exponentials. Like if I ask you, what is the exponential of 1? You know what that is. That's approximately equal to 2.7 something. So, approximately 3. And, from that, what the answer to is, exponential squared, power of 2, that's approximately 9. If I asked you for exponential of, I don't know, 2.7, are people okay with something being raised to a decimal power? You're okay with that? Now, conceptually, it's a kind of it's a more abstract concept than what you are dealing with because, like e squared, that was easy to deal with. You could think of it as e times e, right? How do you conceptualize a number raised to a power that's decimal? That's not, how do you conceptualize something like this? Anybody here? No?
Could you use a linear approximation?
What do you mean by linear approximation?
So you just make an approximation. So what I'd do is I'd pretend that it'd be e to the third power, and then I'd just subtract.
2.7 is not 3.
Well,
so what are you subtracting?
I'd be subtracting 0.03.
So same question. E raised to the power of 0.3. How do you calculate that? Yeah. So I'm asking simple conceptual question. I'm not asking you to use Newton's method. I'm not asking you any calculus question. I'm asking you pre-calculus or pre-calculus question. But the reason many of you cannot answer this question is because it comes down to either you didn't have good math teacher or you weren't paying attention in math. It's one of those two, maybe both. But this conceptual grounding is important as you go to higher level. As you go to higher level of courses, you won't have a laid out prerequisite for you. What a lot of upper division engineering and science and math classes say, what's required is what's called mathematical maturity. It's ability to reason through like this. Not formulas you memorize, not bunch of approximation methods that you memorize, but how to reason through conceptually like this. Chris, you had a question or comment?
You can write it as a fraction, and the top ones are exponentials and the bottom ones are roots.
Yeah, so that's how you would do it. The e raised to power, some decimal power, you imagine it as e raised to power of 27 over 10. Then you can imagine this as e raised to power of 27. We are okay with that conceptually. Raised to power of 1/10. So this is 10th root of this. So we're not going to actually do it, but it's at least doable. So what the 10th root means is that whatever number that is, multiply that with itself 10 times, then you get that, right? There's an algebraic equation you can set up and look for an answer. You can actually do it numerically. Good? So I'm pointing this out to highlight some of the conceptual steps that you have taken already. Because something being raised to integer power, that's kind of the easiest conceptual step that you would get. Like people do this in elementary school, right? Like this is, I sometimes joke about it, but I think this is actually covered in elementary school, raised to power, integer power. And nth root, that's more advanced. That's where you actually have to know something of algebra. So the way nth root would be introduced would be, so if you want to take the e to the power of 1 over n, you would say this is a solution to something like this. It's a solution to the algebraic equation that says x raised to power n minus e is equal to 0. Then this x is this number here. Right? So this, starting with this, it begins to require algebra. So it's probably covered in middle school or high school, depending on the sequence you're on. And now once you know this, then you can express this in terms of fractions, and combining what you know from elementary school and what you know with algebra, you can express this. So I just want to highlight how you go from allowing only integers as power to a number. You expand it to allowing fractions to a power. And once you can do that, then you start allowing decimals. And once you start allowing decimals, then it's not too far of a step to start allowing the complete set of real numbers. Because you just imagine approximating this with just large enough set of numbers. If it's a 2.7, I don't know actual e, 2.7135, then you would say, okay, it's 3 raised to 27,135 divided by 10,000. Like that's how you would conceptualize it, right? So this is the way you have already expanded this function. You have already expanded this function exponential raised to some power x. So let me call this function f of x, where you express it as exponential of x. You've already come this far, where x used to be a member of an integer only. It had to be a natural number. And you went as far as, from what you already know, you went as far as letting it be a member of a real number. And what we are going to do now is simply one more step. We are going to expand this function, the domain of this function one more time to allow x to be complex number. Rather than just real number, it can now actually be complex number. You might wonder, how do we do this? And you are actually given the formula for doing this way before you had the tools for understanding it. Because I mean, when I took trigonometry as part of pre-calculus sequence, not here in SoCal, but that's when I first saw it, so I know it's covered in pre-calculus. This is the equation that you are given in trigonometry or pre-calculus without any explanation. It should have been given the name Euler's formula. Euler's formula says this. It gives you this weird expression. E raised to power, so this is the Euler's number. I mean, what I've been using, but I just want to be extra clear. E raised to power of I times angle theta is equal to cosine of theta plus I times sine of theta. How many here have seen this in trigonometry, or you remember seeing it in trigonometry, right? Yeah, and in trigonometry, we kind of have to give that to you as a fact without driving. We have to just tell you, that's it, memorize it, use it in your homework, and get an answer to that. What I can tell you is that I don't know if this was pointed out to you when you are taking Math 3B, which is prereq to this class, so you should have taken Math 3B. But within Math 3B, you are given the tools to actually prove this formula. How many remember seeing that in Math 3B? Okay, many of you apparently haven't seen it, so let me just go through that quickly. The tool that you are given in Math 3B is Taylor polynomial. You are given a tool to approximate a function in terms of polynomial. Because here's really what it comes down to. Here's the reason you are it's even a question of why it was difficult to expand this into domain of real numbers. Is that this whole raising to power thing, it's complicated. If we could approximate it as a polynomial, then it would be simple because you can take any number, whether it's an imaginary number or whatever, you can raise it to an integer power. So when you are dealing with a polynomial, you can take any number as your domain. It's no problem to use complex number as your domain when you are dealing with a polynomial function. So if we could take some function and express it in terms of polynomials, then that would be a way we can sort of see what the natural extension of this special function will be over a previously unapplied and unknown domain. So let me try to write that out. So what I'm going to write out is the Taylor polynomials of these three special functions you see on the screen here, or on the board here: exponential, cosine, and sine. So let me write down the Taylor polynomials of, Taylor polynomials of this. I'm just going to do it from memory. But I mean, reminder of what Taylor polynomial is. Given a function f of x, this can be approximated as, let's say we are approximating around x equals 0. That's the Taylor series, right? Okay, so around x equals 0. So I can approximate this as f of 0 plus f double prime over 1 factorial times f, not double prime, f prime evaluated at 0, right? Plus f second derivative 2 factorial times f double prime at 0 plus, write down one more, but you see the pattern, right? This is the pattern, and plus dot dot dot. And if I make this an infinite series, then within the radius of convergence or whatever, this equality actually holds. Right? So let me write this down. I can actually write it down just from memory because these derivatives of the exponential and the trigonometric functions, they're kind of easy. So I can actually do this in my head without writing it all down because all the nth derivative of exponential will just be itself. So wait, I did something wrong. Okay, I know what I did wrong. X. Okay, that's what I did wrong. X squared. So this is the actual polynomial part. Right, so this is a polynomial in terms of x. Good? Yes? Okay, so let me do it for exponential. So exponential of, let's say exponential of x. So it's going to be exponential of 0, that's 1, plus, take a derivative, plug in 0, that's another 1. So it'll be 1 over 1 factorial, 1 times x, so plus x, plus 1 over 2 factorial times x squared, plus, let me actually write out the 2 factorial, so that's 2, plus 1 over 3 factorial, so 3 times 2, 6, x to the third power. I guess let me write down one more so that the next step will make more sense. So 1 over 4 factorial, that's 4 times 6, so 1 over 24, x to the fourth, plus, and so on. Right? That's exponential as a Taylor polynomial. Okay? So when we imagine extending this function into the complex domain, this is what we are doing. We are saying, instead of saying this is x, let's say this x becomes, wait, do I want this color? I want something more distinctive. Let's do red. Instead of x, let's say wherever I see x, I'm going to replace with I times theta. Because I frankly don't know what this is. But the right-hand side is something that I can evaluate. So let me do that. Plug in I times theta here. Plug in I times theta. I times theta. And I times theta. And then, it'll go on forever. But here's one thing nice about I. The imaginary number I has a pretty nice property, algebraically speaking. Because of this, the most unique number of values that a power of I can take is, I guess, at most 4. So, I to the power of 0 is 1. I to the power of 1 is I to the power of 2 is equal to minus 1. I to the power of 3 is minus I. And then you take I to the power of 4. That becomes 1 again, and so on. So when you imagine expanding this out, so, I to power of 1. And then I to power of 2 over times theta to power of 2. I to power of 3, theta to power of 3. By the time you come around to the 4th order, this I to the 4th power will simply become 1 again. So you can actually, let me write out this term. So when you write out all these terms, this is what you get. 1 plus I theta. I squared is minus 1. So minus 1/2 theta squared. And I to the 3rd power is minus I. So minus 1/6 theta to the 3rd power. And this is 1 again. So plus 1 over 24 theta to the 4th plus and so on. And so I forgot something. Oh, this should be minus I. Minus I theta to the 3rd. So all the terms, they can be categorized into one of two categories. The terms that do not have I, imaginary number in them, and the terms that do have the I, imaginary number in them. Okay? And if I wrote out one more term, I really should have gone one more term. So the 3rd or 5th term here would have been I to the 5th power. So it'd been plus 5 times, let me just write it down, 5 factorial times I theta to the 5th power. And then, plus and so on. So you can divide it into these two categories, terms without I and the terms with I. And once you simplify everything, the most power of I you would see is just 1. Right? That's what you see here. Most power of I you need is 1. So let me separate this out with the terms that are real and the terms that are imaginary. Let me just to do that and see what we get and see if we recognize anything. So these are the terms that are real. 1 minus, I guess I'll write it out in terms of factorial again. 1 over 2 factorial theta squared plus 1 over 4 factorial theta to the 4th. And then, if we keep going, it'll be minus 1 over 6 factorial theta to the 6th, and so on. That's the real terms. Plus the imaginary terms. Since they all have I in it, let's factor out I. So we can just have I by itself in front. So it'll be I times the rest of the terms. So theta minus 1 over 3 factorial theta cubed plus 1 over 5 factorial theta to the 5th power. And then if I keep going, it's going to be minus 1 over 7 factorial theta to the 7th, and it'll keep on going. So it neatly separates that out that way. It's, I guess, the nice property of I. Now, it's at this step where you might actually recognize what these are. Do you recognize what this looks like? Have you seen this particular Taylor series before? Yeah, if you don't recognize it, you'll just have to work it out on your own and just to confirm it for yourself later. This is the Taylor polynomial of cosine of theta expanded around the theta equal to 0. You can check it for yourself later, go through this formula. I won't do it in class, I'm already running out of time. And knowing that, what do you think this is? Yeah, this is the Taylor polynomial of sine of theta. So this is Taylor polynomial of sine of theta. So that's where this formula is coming from. When you evaluate this and expand it out in terms of Taylor polynomial, you get these two distinct terms. And it's not always the case that you can say, oh, so this is equal to this plus this. You have to worry about convergence. It's usually mathematicians who worry about that. All these functions have infinite radius of convergence. Exponential has infinite radius of convergence. The trigonometric functions have infinite radius of convergence, so you don't have to worry about if like they are conditionally convergent or whatever. But okay, let me not go into that. But this is the justification for this formula that you are given before. And what I'll tell you is that this complex exponential is one of the most useful functions when you are dealing with, when you are dealing with advanced level physics and engineering. When you are dealing with circuits, this is actually one of the most important functions. It's so important that electrical engineers, they worry that this I will get confused with the current, that they have this convention, they let J be the square root of -1. It's because they can imagine doing their work without complex exponentials. So they would rather change the letter they use for so that they can actually use it.